here in this seminar is Giorgio Krstulovic. It's okay? He is master undergraduate here in Universidad de Chile, and after that his PhD was in Historia de Paris. And after that he got a PhD position, postdoc position in East, and after that got the seminar position in East. So thank you for coming. Thank you for your
thank you, Jimena, for the invitation and the introduction. So I'm Nis, as Jimena said, in the Observatoire. So, but I'm not a astrophysicist. Okay, I'm a physicist. Okay, I do theory and maths. And today I'm going to talk about turbulence. So I looked more or less on the website and I saw that you are all from very different fields. So none of you is an expert in turbulence, if I'm not mistaken. So please, at any time, just interrupt me. Even if there are some things that I might think that are very basics, because I'm in years. But please just tell me, and I can go even to the basics if I don't get it to the end. That's okay. So they just have to deliver a good message and tell what I'm doing. So also feel free to ask in Spanish if you want. I was born here, so it's not that much. So as I say, we'll talk about turbulence, but not only turbulence in a classical fluid. A classical fluid, you might imagine water, air, okay, which is a sphere and has a lot of eddies and vortices. Okay, it's turbulence. But I will also talk about quantum turbulence. Okay, quantum in the sense that the fluid will be quantum. It will be a superfluid. Okay, which I will define. I will tell you what it is in a couple of slides. So I have to say that this work was mainly done by Juan, was my postdoc, okay, and Nicolas was my PhD student, and I'm actually very proud of it because it's a full Latin American work. Juan is from Chile too, okay, he's in Católica now, the CNRS research in Enero, and Nico is from Buenos Aires. So it was very fun, and all what we are telling today was done during COVID time. So it was everything done online at the beginning. We continue. So what is turbulence? Okay, if you want to talk about turbulence, the simplest is so either you look at this type of numerical simulation. This is now rather old. It's almost 20 years old. Okay. So what you're looking here is vorticity. Vorticity is just the curve of the velocity. It tells you how strong the fluid is rotating. Okay. So you see that this, if you look at here, this is kind of a structure that's very thin filaments. So those are bits numerical simulation at the time. Okay. So this is the full computational box. Okay. You see this kind of very complex structure of vorticity. If you look at it in square and you zoom in, you will look the things look the same. Okay, if you take another square of the simulation and start zooming, you kind of see this self-similar behavior when we are scaling. Okay, until you are a very small scale and you can really visualize a very fine structure of that small vortices, like small tornado. So the Maxwell's equation describing turbulence in the simplest way is a Navier-Stokes equation, and then usually we assume that the fluid is incompressible. Okay, this is the standard. And there is one dimensionless number that tells you how turbulent the flow is. It's called the Reynolds number. That is basically you take the vector term, okay, and you divide it by the distance. This is just obviously you have to put proper line scales, okay? And those are vectors, so it's not a formal division, but they give you an order. So typically, if you do so, the Reynolds number is basically the typical velocity of the flow times the length of the object moving divided by distance. And we talk about turbulence when Reynolds was continuous. Okay? Otherwise, in a fixed container, okay, you can the way to reach turbulence, you have a washing machine. Either you change the fluid and take something that's less and less viscous, like you try to stir honey in a washing machine, the fluid never will be turbulent. But if you do it with water, there is a lot of turbulence. This is changing it. Otherwise, if you inject more power, this means increasing U, that's increase Reynolds, and you start developing a lot of turbulence. Okay? This is the overall view of turbulence. If you want to play a bit more with the equations, okay, and you look at the kinetic energy, so yes, V is the velocity. The mass, we assume that is constant density equal to 1. Okay, so energy is just, the kinetic energy is just 1/2 v squared, which is a constant quantity if you don't have viscosity and forcing in the other equation. And you try to write an energy balance, it's very simple. The variation of energy is just the input minus the dissipation. Okay, what gets in gets out, and that gives you a balance. And the energy dissipation rate, you just need to play a bit with the equation. It's related to nu times the vorticity, the curve, okay, the gradient of the vorticity. So this is just you multiply by V, do an iteration by part, and you get the balance. But the tricky part of turbulence, and perhaps the most difficult, is what's called the zero law, okay, which means that when you take Reynolds going to infinity, okay, dissipation is finite. Okay, this is a bit strange in turbulence. So what you are doing is taking viscosity that goes to 0, okay, which is the parameter that is dissipating, okay, and still you get some dissipation in the system. Okay, and if you look at the definition of energy dissipation, is nu times the gradient. Okay, it means if nu goes to 0, the gradient has to go to infinity. Okay, and this is turbulence. Okay, a really fully developed turbulent flow is something that has infinite gradients. Okay, in any experiment, nu is finite. Okay, and the flow is a very small scale due to viscosity. But if you want to realize turbulence, this is the demand flow with infinite gradients. Okay, and this is something. It's not just a mathematical construction. It's something that has been tested numerically in experiments. Okay. What I'll show you here, it's some dimensionless way of measuring the dissipation of a function of Reynolds. Okay, and experiment to see that indeed, if you go to Reynolds high enough, you get to a plateau. Okay, it means that the flow is really turbulent, and actually in all what's turbulent, the dissipation doesn't play any role. Okay, it's all driven by the nonlinear test, which creates. And this has a very important consequence: the fact that you have a finite dissipation in the system, okay, which is given really by the gradients that are infinite and the nonlinearity, which allow you to sorry, this is what I was saying, okay, that when you go to 0, okay, you still have a dissipation, and this is called a dissipative anomaly, okay, a name that is taken from quantum field theory, because you have a symmetry breaking parameter, and you don't recover the symmetries when you take the symmetry. But this is known in the field of dissipative anomaly. But the fact that you have this constant rate epsilon, okay, brings you to the idea of turbulence that was introduced by Richardson and later from Alain at the beginning of the century. Then that when you have turbulence, you have a cascade of energy. Okay? So what is turbulence? Suppose you are stirring, okay, your coffee with a spoon. Okay? So you're injecting the energy typically at the size of a spoon. Okay? And then because the system is nonlinear, it will generate three eddies, vortices at the scale of the spoon, and then those will interact nonlinearly and create eddies at a smaller scale. Those will also interact between them at that scale and will create others that are smaller, and smaller and smaller and smaller in a cascade process. Okay? This picture of cascade was included by Richardson, is really the cornerstone of turbulence. So the idea is, okay, this will happen, okay, as anticipating with a flow with a rate, energy rate of epsilon, okay, injects have to be the same, and the energy have to be at the right, okay, those states. Now, and the limit, of course, that I have an infinite separation of scales between the scale at which I'm injecting and between the scale at which I'm dissipating. In between, I expect to have something universal that only depends on the properties of the field, and that's turbulence. And actually, turbulence can be very complicated. but can be also easy to give some phenomenology. So under this assumption that you have a scale that are much larger than the dissipative scale of the system, okay, which is given by viscosity, and much smaller than the scale at which I'm injecting, I expect that the only thing that can be relevant to describe turbulence is this final dissipation, this transfer rate. And then in physics, when you have just only one dimensional parameter, the simplest thing to do is a dimensional prediction. Okay? And dimensional analysis tells you everything. Okay? So for instance, you want to look at a way of measuring turbulence is what is called the velocity interval. Okay? It's a type of correlation function. I'm taking the velocity at point x, and I will look at point x plus r, and I will subtract the velocity field. Okay? So with that, I'm looking at how the velocity will vary at a given scale. So suppose we are all moving with an overall global mean flow. Okay? If I look at the difference at the scale r, I'm sampling how the velocity fluctuations are at a given scale. Okay? And this gives me a measurement of velocity fluctuation at the scale of observation. And if I'm in a more homogeneous system, the same with respect to the independent of x. If you want to do dimensional analysis, okay, data is a velocity, so that's a dimension of a length over a time. Okay? The energy dissipation rate is an energy over a function of time. I don't have mass, so it's an L square, length square over times cube. Okay? If you look, for instance, you want to give a dimensional prediction for the variance of the kinetic energy at the scale r, well, it's simple. You don't have too many choices. Okay? You need to match, so this has dimension of L2 over 2. You don't have any other dimensional choice that take epsilon to third and L to the 2 third. This is just pure dimensional analysis. There is no calculation. And this is due to Kolmogorov already in something that was already understood in the focus dimensional analysis, based on the fact that in this inertial range, at those scales, the only thing that is relevant is the transfer of energy along different scales. And this is finite when you take the range of infinity. So I'm taking range of infinity to get rid of boundary effects and this. And so this is the prediction in physical space. You want the energy spectrum, it's related to Fourier transform, it gives you what is known as the -5 vector. That is two predictions are completely equivalent by Fourier transform.
I have a question. So the value spectrum is the Fourier transform of S2.
Yes, with respect to R, exactly. So then this is a kind of trivial so assuming that you have proper boundary at the limit in order to make the integral converge, but it's just so this is not mathematics. But anyway, this is not a hard result, it's just dimensional analysis. Saying that at those scales, the only relevant parameter to describe the fluctuation is epsilon, this energy flux, and the scale of observation. Is this the only two things that I have? I don't have any other choice to build this quantity dimension. Okay? And what I show here is a picture taken from the book by Yuri Frisch. It's an experiment which is quite old by now. It's of this probably of 60s, 70s, okay? Where even at that time, I'm looking here the log of S versus the log of L. Okay, so power laws are straight line, and they observe that they have this very good. So this scaling law is something that's kind of very well established now in journals. Okay, in any engineering application or theoretical, if we observe this, sometimes plus some correction that we can understand. Okay, so I say that turbulence is very complicated, and I'm just getting a result using dimensional analysis. Okay, so if I took the variance, I get the scaling, I could go to high order moments, high order correlations. Okay, so instead of taking the power 2, I could take the power p. So this is a way. If I look at moments of a fluctuating field, if I look at high order moments, I really sampling the tails of the distribution, so it's a more extreme event. That's why we have the interest for looking at different moments. Same dimensional argument will tell me I just have to replace the 2 by p in order to match dimensions. Okay? And this phenomenology, dimensional analysis, just give me that. But in general, what has been observed also in experiment mathematics, that this is, so if you look at the exponent here, okay, you see in general, you can expect that this order p, or like some zeta p, some exponent. And if the physics is completely self-similar, okay, it's simple. This will be a linear function, but in the Krstulovic surface is a non-linear function. Okay? And these are experimental measurements. This is one of the most challenging things to understand in turbulence. Why we have such a strong correlation and a breakdown of such similarity. Okay? And this is called as intermittency. Okay? So it's the emergence of very extreme events in turbulence that really kind of breaks the similarity and makes things very complex. And we understand it's related to dissipation, it's not continuous. Okay? So we need to account for strong fluctuation of dissipation field that acts and a change of the statistics. Okay? So this is more or less the picture and the only thing I would like you to understand about turbulence. Okay? So we look at scaling laws. This is what we do as physicists in turbulence. We want to try to understand these exponents. We call them anomalous exponents. Okay? Because they don't follow the trivial conditions. And so now I can jump to superfluids, quantum. Okay? So I give a very short introduction to what we are doing in turbulence. Now I want to say what is quantum turbulence. There will be turbulence of a superfluid. What is a superfluid? It's a fluid that has no viscosity. Okay? And what I mean by no viscosity is not that it's small, it's identically zero. Okay? And that's possible because there is quantum effects in it. Okay? The oldest superfluid we know is helium. Okay? Helium that we use for balloons. Okay? But when you put it down, okay, at below 2 kelvins, it becomes superfluid. It goes through a phase transition and it becomes superfluid. Okay? And this was seen by Kapitsa Allen in the studies. Okay? And in this phase, at very low temperature, it really flows without any viscosity. Okay? Can cut with no numbers. This phenomenon, why this happens is something very closely related and exactly to the phenomenon of Bose-Einstein condensation. Okay? Something that we learn in statistical mechanics. Okay? Which was predicted by Bose and Einstein at the beginning of the century and only observed experimentally at the end. Okay? So when you have this type of fluid, now it's in laboratory it's very doable. You can excite them, okay, and play with this type of fluid and start looking at the dynamics. So what I'm going to show here is a movie simulation. Okay, I will tell you in a minute what is the model that I'm using. Okay, but this is just a zoom of what they're going to show. So I'm going to tell you this. This line here corresponds to vortices. Okay, vortices are like small tornadoes. Okay, if we are thinking about helium, this would be the size of an atom. If we are thinking about a gas of Bose gas, this will be a couple of micrometers. Okay, so those lines are vortices. Okay, the yellow things are density fluctuations of the fluid. Okay, and what I want to show is that it's an evolution of how it works. Okay, you look at very deep inside, you see that these lines reconnect and change. But if you look from outside, okay, you can kind of recognize a kind of fluidish behavior, okay, where there is a large scale flow, like if you were on a classical fluid, okay. But however, at the beginning, the fine liquids inside, I really think that are very different from that. Okay. So if you want to be very pictorial in the description of quantum turbulence, what it is, okay, it's a superfluid, it has no viscosity. Okay, we'll tell what is the model in a second. Okay. They are compressible, so there are some ways to propagate around. Okay, they are actually dispersive. Well, it's a quantum system, so you typically describe it by a complex orbital parameter. And they have quantum vortices that are filaments, okay, and they are always present when you excite a superfluid. Okay, you put some energy in it, and they will nucleate a lot of these vortices, and you reconnect. So to understand a bit better what is a quantum vortex, the simplest way is to think about a tornado in a classical fluid. Okay? So a tornado is a region of the flow where vorticity is super high, and it's very concentrated and very localized. So a tornado typically you can associate a circulation around, which is the line integral of the velocity across the sky. So this is a measure of how much is rotating the fluid around. Okay? And this is a real number for a classical velocity. And each tornado curve has a typical core size. Okay, it's called the psi. So quantum vortex, the way to visualize this is okay. We take this tornado, take the core size core going to 0, but keeping the circulation fixed. Okay, and you get this kind of quantum objects. Okay, and that makes sense because actually they are topological defects. Okay, like in the I was saying helium typically the size is an Armstrong. Okay, in a Boston synchronous it's an electron. Okay, and the particular case quantum fluid that this circulation gamma, yes, it's not actually a real number. The number is quantized. Okay, and this is because of the pure nature of quantum mechanics and the topological defects. So experiments on superfluids. Okay, what people are doing today. Okay, so what I'm looking here are the scales at play. So the smallest scale we can say that is the size of a core. Okay, if you think about helium, we are talking about an Armstrong. Experiments with turbulent superfluid, for instance, this huge Schrodinger experiment in France. It was a container with the meter size. Okay, you cannot see it very well, but here is a person standing here. Okay, so there were about 800 liters of superfluid helium. So at less than 2 kelvins, when you put a lot of power. Okay, so the idea is the following. Here, if you're looking at that scale, it's the intervortex systems, typically between elements. If you look at scales that are much larger, you don't care about this nature of these vortices. They are just filament, but you are looking from very far. You kind of take this image. So here, the projector helps to really blur everything of this filament, and you see a kind of general description of a fluid. And what applies this idea of cascade. Okay, so if you inject energy at the largest scale of the system, you expect that the energy will be transferring along the scales with the same idea of the one. This is indeed something that has been observed experimentally. But when you are at those scales, then you start seeing quantum mechanics and the filament that become split objects, and there are other mechanisms to transfer energy. Okay? For example, this picture here shows an experiment visualizing in such a quantum mechanics. So how do we describe quantum turbulence? We use the so-called Bloch-Pitayevsky equation. I don't know if any of you is familiar with that. With this equation, have you seen it before? You have seen it. Okay, or the NLA nonlinear Schrodinger equation, yes, and the concept of optics. Okay, so this is an equation that really don't look like a fluid equation. Okay, you cannot imagine that there is a fluid described by this equation. It looks more like a wave equation. In particular, there is one steady state that's given by a constant amplitude and a phase oscillating. Okay, this is a constant solution. You can perturb it. Okay, and do linear analysis, and you get this dispersion relation of the frequency of the waves with the wave. It looks very complicated. You have each bar, blah blah blah. But if you want to just simplify it and redefine things, dispersion relation looks like this. Okay, so you look at large scale, so that means very small k. You can neglect this part. Okay, it's more than side, which is that actually we did the side before. This is just like sound waves. Okay, propagate like normal sound. Of course, everything is a very small scale. Dispersion that's coming from this part starts to act, and actually it's useful to regularize this. Now this is a nonlinear wave equation. Okay, so where are the vortices? Where is the fluid? Well, there are fluids. There is a fluid kind of embedded in this equation, and you write psi, which is a complex field, in terms of a density field and a phase. You just plug it here, okay? And I'll take a real imaginary part of this and get these two couple equations. So you can recognize here that it's the field rho, which is the density, is transported by that phi. Okay, so you can say, okay, that phi will be the velocity of my superfluid, and phi satisfies something that's very close to the Bernoulli equation. Okay, plus of course something like here that is this equation. Oh, fine, nice. This really looks like a fluid, but velocity is potential, and I've been talking about vortices all the time. Okay, so naively, if you take the curve of the vorticity, the curve of potential is zero, a priori, but not if the potential is singular. And this is what it happens. Okay, suppose now that the psi has a zero in some point of the space, like here. Okay, if you ask what is the phase of a complex number 0, the phase is not defined. Okay? So if you have a 0 of the complex of the wave function psi, you can have the phase as a branch of discontinuity. So such that if you do the line integral of the gradient, okay, it has a jump. Okay? But as the phase is phi is the phase of a complex number, the jump has to be compressed in order to make the function more orderly. And that gives you that the circulation, as the system here, has to be a multiple of some number, the quantum circulation, just to make everything complete. Okay? So here, naturally, if you have a 0 of this field psi, it's quite natural to expect to have a work of them, okay? Provided that the phase is grounded. And as we are looking at the zeros of psi, if we are in 2 dimensions, so psi 0 means the real and imaginary part of 0, so 2 equations in 2D will be points, and that will be lines and 3D. Okay? So basically you get from here, if this is constant, okay, it means that the velocity goes like 1 over r. Okay? So this is the type of fluid you are having. If you take the vorticity is not 0, it's a Dirac. It's not zero. This is in 2D. But in 3D, you can imagine that it's like in electrodynamics when you have a wire and you want to compute the magnetic field from the turbines. So you have to use a lot of. So basically, this is more or less all what you need to know from superfluids. Okay, then now the later I will start looking more on the. So if you think about Krstulovic as a model for superfluid, and you are looking at the vortex dynamics, you have to imagine that it's a collection actually of ideal vortex lines. Many vortices that they interact with each other like 2 tornadoes will. So you have 2 that are co-rotating in the same direction, they will just move, they will advance. So it's the same direction they will rotate. If they are in different directions, they will advance. And basically each line will feel the velocity field produced by all the other lines in the system and will move. Okay? So the idea, the simplest way of visualizing this is just filaments that are following gears around the world. And this is because the velocity fields were like one. There have nevertheless a finite course lines that's given by the dispersion of the system, which allow the vortices to reconnect and regularize everything and have a nice and smooth dynamics. So with this idea in mind, okay, we can do numerical simulations, okay, and try to get quantum numbers. So what I'm showing here is the same equation, it's slightly different, the detail is not important. And to do that, what we do, okay, we go to the big clusters. Okay, we go to GenSig, which is the National Center for Computational for HPC in France. Okay, so you put this equation in a quick machine, okay, and start simulating. Okay, so here this type of simulation has 2,000 points in each direction. Okay, and what I'm looking here is that the whole field, okay, and the whole computational box. Okay, I told you before that there is this classical scaling law for the induction scale up to the intervortex distance, and then there is the vortex size. So here I'm taking the sub-box here is what I'm showing here, and the intervortex distance corresponds to this very little scale. So it's kind of very big simulation. So this is basically the state of the art numerical simulation.
You are including some interaction potential.
Here, yes, this is.
What kind of potential are you?
This is something that we use to mimic helium. Okay, so you can imagine the symbol you can use is a heavy side. Okay, will not change much. Okay, so this is a particularity of helium, and you see that it's also high order non-linearity.
So the potential depends on the material.
No, the potential here is actually this is modeling the interaction between atoms.
Ah, okay. It's for first principles.
Yes. Okay. Yeah. So the simplest, so the original equation comes from an approximation when you say that you can replace this by a Dirac.
Similar to a DFT potential.
Yeah. Okay. But here, it's really this is something that actually at very small scales and it plays no role when I'm telling. Okay. And we do that because in helium, if you want to be closer to helium, okay, the dispersion relation of the waves is just not like a phonon branch going to space squared. It has something called rotor minimum. Okay, this is really something more complicated. And the shape of the dispersion relation is actually given by the Fourier transform of this interaction potential. Okay?
And also you have some gamma factor
Yes.
in the last term.
And
What
this is
the-
also to mimic the equation of state of helium. Okay? Because if you don't add it, okay, this model have tendency to crystallize and it can become unstable. Okay? But also basically because helium is rather uncompressible fluid, okay? And if you don't put it here, the system is really compressible. It's to be a bit closer, but in practice doesn't play any role.
What is the value of the gamma?
It was a bit smaller than 3. Okay? But really, the details of the model are really not important. Okay? Okay, the idea is we use huge numerics, okay? Because we want to look for scaling laws, okay? We need to watch for a scaling laws, and scaling laws are always polluted by the size of the box and the smallest scale, that in my case here is helium. So I need to put here, in practice, a couple of grid points of scale. So that's why I need such a huge resolution. Okay? And the only way of achieving that is to put it in an analysis. When you do that, then you can look at the energy spectrum, okay? And you observe that there is a classical regime where you observe tomorrow. This is the intervortex system where something happened. I will not discuss. And then there is something else due to the physics of this pyramid itself. With 5 chance has the same scaling, but there is here we have some very good analytical theory. Okay? But I will be more talking about this. And I want to look at it in a different way, which is use circulation. Okay? So I told you circulation is a line around a closed loop. Okay? For instance, here you can take circulation and this loop. I could take a path that is surrounding my whole computational box. Okay? Or I could look at a loop that is enclosing maybe 2 or 3 vortices. Okay? So the idea is I will look at the circulation on a loop, okay, of area A. Okay? Or if you want size, typical size R of radius square root of A. I will take square, the shape it really doesn't matter. Okay? And the natural idea is to ask what is the statistics of circulation as a function of scale. By symmetry, if you look at the circulation, so what in practice what they will do, we take data, we take a loop, we take the flow, we compute circulation, okay, for a fixed size A, and we'll repeat this everywhere in the box, and then that will generate a statistical ensemble where I can use dimension. By symmetry, if I just look at the mean value of circulation, is 0. Okay? The fluid is not rotating in average. Okay? But if I look at the variance, this will not be 0. And you expect that this will scale with some power. So let's say the circulation square will scale like the area to the power lambda 2. Okay? And the question is, what is lambda 2? Okay? So again, this is turbulence, and you can do dimensional analysis. Okay? Circulation, what is the dimension of this? Is a length square, circulation square. Okay? What is the dimension of that? It's an L square over times square. So L4 times square. Okay? Again, if I'm in turbulence, the only relevant parameter is epsilon, because dimension of L2 over T3. Okay? And I'm asking this to be a function of the area that is L square. Okay? If I want to match dimension here and here, I don't have any other choice than take epsilon to third and take it as well. Okay? This is dimensional grounds. Okay? And actually, it is something that was observed a couple of years ago. And this is a huge Navier-Stokes simulation, okay, done by the group of Fire and Chemia. So here it's, I think, so it's Reynolds lambda. It's very high simulation. I think where I don't remember if 8,000 or 16,000 cube points. Okay, so it's really, really massive. And what they observe, almost like an astrophysical measurements, many decades of scaling, but this was only made with a beautiful 2/3 scale. It is 2/3 not 4/3 because they were taking the standard deviation, so they were taking the square root of this. Okay? So actually, when we saw this result, it's really inspiring. Okay, so they took Navier-Stokes, observed such an amazing scaling laws, and I say, okay, well, we should do it in quantum turbulence because their circulation is quantized. Okay. So now for now I take the quantum circulation to be 1. So circulation is an integer. Okay? you have a loop size R. I just need to count how many lines are crossing this up and down. Let's just make a sum. Okay? So if I have this and each line you can substitute with a plus 1 or a minus 1. Okay? Okay, circulation maybe 1. Maybe now circulation is 0. Here is minus 1, and then when you have many lines, it looks very complex, but in the end, expression will be just 2. Okay? So if you remember, you are adding plus and minus. This kind of looks like a spin model. Okay? And this is the simplest thing you can try to understand. It's okay. I would imagine now I don't have a space dimension. Okay? But I will have my vortex, like a spin. Okay? Circulation will be just the sum of my S, where S is plus or minus 1. And I will sum in a box of size R. I will have typically N. Okay? Typically, this is just the number of vortices I have. This is homogeneous. Have to scale as the area. Okay? So I can relate N to the area like that. If I want to compute the variance, okay? Well, it's simple. I split the sum of I equal to J, and I different from J. Okay? This is always 1, so the variance will always be N plus the sum of all correlations. Something that I don't know, obviously. Okay? But you can immediately get something simple. If there is no correlation between vortices of spin, all these turn out 0. Okay? And basically, gamma squared equals like N. Okay? What does it mean? It scales the number of vortices. This is a random walk. Okay? Everything is decorrelated. And the correlation the circulation you can treat as a random walk. On the other hand, if everything is correlated, say are all of the same sign, then circulation will be N squared. But turbulence has a different scaling, okay? And it's 4 term, something in between. Okay? But it's telling you that turbulence is such that there is a very precise correlation. Okay? You cannot see it much, but here we color those vortex lines in this big simulation with respect to the orientation, up and down. And you should kind of see here there are bunches of green and bunches of yellow, showing that there is some correlation that is related to hydrodynamic temperature. So, and they are in some sense polarized. So, with this idea in mind, you can kind of construct a very simple model in which you want to have a toy model to deduce things. Okay? So the idea is you will consider the same way n vortices in a loop. Okay? Okay? I will choose the first one randomly, plus or minus 1 with the same probability. And once I have n of those vortices, the next one will be biased by the mean circulation of the system. Okay? So let's say if the first one is plus, okay? So then the second I will show is more likely to be plus and minus. So let's say that the second one will be plus, okay? So now the third can be still a minus, but it's less likely to be, okay? So plus more I have on the same sign, okay? More likely to be the system. So this I'm putting a correlation and hand in the system. And in terms of a transition, it's just to say that the n plus 1 vortices will be 1 with probability 1/2 plus the value of the mean value of all the neighbors, 125, which is our mean. This is called actually a bias from the north. So there is correlation between all. So in the end, when I have my n vortices, there is a strong correlation between all of them. You can compute it analytically, and somehow we will do it. But now the next things about this, okay, they are all correlated, but if you look at now circulation, okay, as a function of n, it only depends on the position or the value of the circulation on the previous step and the new thing. So this is a Markov chain. Okay, Markov process, when you have a Markov process, you are done. There is a lot of things you can do. Okay? So you can write an answer equation, that I will not write, but you can take the continuous limit in n to make things just easy here. And you get, for instance, for the variance, a closed equation that you can solve. And that has basically depends on beta. Okay? If beta is not large enough, large is 1/2, everything is dominated by diffusion, so you get this diffusion. Otherwise, we get some power. Okay? Particular beta to third give you the common. Okay? So this is a toy model. It just shows you that the fact that there is this particular correlation between the vortices allow you to actually recover from that. I don't know if I will have time in talk, but basically we use this model then to look a bit deeper in detail. So what we have to do now is actually take our big super quantum turbulence simulation and look at the circulation and how we do that. Okay, here there is a piece of the box. Okay, it's not the code simulation. And what we do, we take a loop. Okay, we take a slab of my box. Okay, and I compute the circulation at a given size. Okay, and I have to be careful because phase each of these points is a diverging thing in the velocity field. You have to do it numerically, it's a bit tricky. Okay, so we do it with some techniques into the details. But basically, for each slab like this, I compute loops of all possible sizes in each point. Let's give you an ensemble, and then I move slabs. I scan slabs in the whole box and all directions. So I have a kind of very good statistics. And that's what I'm showing here. So this is the PDF. So you look at very small scales. I get discrete PDF, okay, which you expect. So basically, you will get a vortex or not. Okay, maybe you at scale. This is an R over the mean distance. So if I'm at very small scales, I either get one. The circulation is either 1 or minus 1. I can get only one vortex. But as close I get to one, circulation can start taking large values. And if I look at very large scales, okay, something like this, the PDF becomes continuous, okay, and start looking a bit of similar to what has been observed in this. Well, with this data, I can compute moments, okay, in particular the values, and it's what you observe. Okay, so there are two amazing power laws in the dynamics, okay, for more than 1 decade. So there is indeed a region where I have the scaling of Kolmogorov in this simulation. That is here, okay. It's telling you really have Kolmogorov turbulence in this cross-beta ESP system. And this is another very nice scaling here, okay. And this is actually very simple to understand. You are scaled much more than the intervortex systems, okay. So when you look at loop is very small. So either you will enclose a loop, at which case equation is 1, okay. Either is 0. And that, so the probability gamma will be 0, will be 1 with probability of a loop of size r enclosing a loop, and they just simply the area. Okay? And basically you get the scale. If you compare with Navier-Stokes data, okay, you get exactly the same scaling law at this range. Then obviously you have a different scale at most scaling at small scale because this is given by viscosity. And this is given by the nature of this quantum vortex. But if you look here, we have the same scale. And the thing, do not stop there. Okay, you can go a bit farther. Okay, and you can look at the intermittence. Okay, I look at the p equal to 2. Okay, and in general, so the dimensional prediction will tell you that if you take the variance to the power p, so you're really looking at the strongest fluctuation, the short scale like 4p. Okay. But in general, you expect this to be a nonlinear function of p, as we know that what's happening here. And these are different moments. Okay, on plotting here is what's called the local slope, it's the logarithmic derivative of the moments. So if the logarithmic derivative is such that if you have a pure power law, this will be flat. Okay, and this is what the point here. So it doesn't look very flat, but for people doing turbulence or looking at power law, this is extremely flat and well converged. Okay. And I'm looking and going up to p equal to 10. So the higher the order of the moment, the more statistics are required to make it converge. So it becomes more and more. And from here you can measure those lambda p's, which is the mean value in this region, and you get this quantum distribution. So in the paper that I mentioned before, okay, that's Navier-Stokes, they also tell me the limits. Okay? And they propose a p. So it says basically it's similar up to some p over here, and then has a different slope. So we have basically just took their fits and put it in our data. Okay, and we actually, so here it's kind of very strong result. Okay, so we are looking at two different systems. Okay, and what we said that at all values of p, okay, we get the same exponents. Okay, and this is something that is kind of surprising if you start thinking what really we are doing. Okay? We are comparing quantum and classical turbulence. Okay? So classical turbulence, you have this kind of picture of electricity, okay? That is anyway a continuous field. Okay? Here I have something that really is fixed. So we say circulation in this case is quantized, it's an integer. Whereas here is a real number. So this is very difficult to mind that can be similar anyway. This equation has nothing to do with understanding. This is a complex field, this is an incompressible velocity fluid with a term of This is compressible, this is incompressible. There are some with propagating, here there are not. A very important difference, here in Navier-Stokes there is viscosity, which acts at very small scales and regularizes things. Okay, borders can reconnect because there is viscosity. Okay? Otherwise they are not allowed by chemical. Here there is no viscosity but there is dispersion in the system, which also tends to regularize the system. Okay? So the small scale mechanism that makes reconnection and regularizing is very different in nature. But nevertheless, you have the same. You can look at very high order statistics, and most systems present the same statistical data. Okay? And this is something very strong. Okay? And that was very appealing in the community because it was bringing more classical fluids to quantum turbulence together. So, I will not have time actually, because I don't know how much time I have left.
It's okay. It's okay.
Yeah.
Okay. Can I go further?
Yes.
Okay. So the idea is okay. So now I have established okay that the statistics of quantum turbulence and classical turbulence is pretty much the same, despite all this. But on the other hand, quantum turbulence is kind of nice and simple because I'm just summing numbers. Okay. So the question: can we actually use this to get some more of an understanding of it? Okay. So the idea is yes, we can kind of inspire ourselves of this very simple Markov chain model. Okay. So this is what so from this Markov chain I have this equation for the variance, okay, which gets either n or n beta. You can do the same, okay, for any order, okay, shown analytically that whatever beta you take, okay, you will always have a scaling that is linear with beta. So basically this Markov chain is always a linear, which is not surprising, it's too simple to have to be intermediate, to be relevant for okay? And actually not only for this transition probability, you can put an arbitrary transition probability to bias the process, and always get the same scaling similar scaling. So this is obviously too simple, okay? And why is too simple? Because there is no notion of space in this Markov chain process, okay? But I say, okay, I have n vortices in a box, but the box is at anywhere. It can be everywhere. There is no correlation a priori, there is no fluctuation from one side to another. There is no notion of space, there is no intermittency. But the question, can we take this as the idea of this model and measure things in a different manner in our data? And this is what we do. So, we like to now look at the circulation as a function of the number of vortices. Okay? So we need to give a notion of what it means. So it's very simple to say circulation as a function of scale. I vary the loop and then see how the circulation varies. Here I want to say how the circulation varies when I change the number of vortices. Something like I be closer to the model. And the idea is simple. If I look at a point in space x, I will look at the n closest vortices. Okay? So for instance, here is the n closest vortices here. It's a very small loop. And here the n closest vortices is a larger loop. So somehow I'm really relaxing the notion of space, and I can get now the number of vortices function. It's a different way of looking at the statistics. Okay? It's a different condition. If I do that, okay, then I get the good scaling as a number of vortices. Here I'm comparing circulation as a number of as a function of the area in blue, and in orange as a function of the number of vortices. Okay, and the moments gets the same scaling. So I still recovering. Okay, but the nice thing is now I start looking at the intermittency, the system becomes so simple. Okay, so now if I look at the number of vortices I have, if I look at circulation as a function of the number of vortices, the system is completely self-similar. Whereas if I do it as a function of the loop, is intermittent. Okay? And this was really motivated by the model. So this was a kind of nice result. And actually we understand it a bit. Because this will be a little maybe too technical, okay? But this is something that we know in turbulence that is related to the fluctuations of dissipation. And here we can relate intermittency, we'll skip, but the fact that even if the distribution is homogeneous statistically, it clusters, okay? And the cluster is what's called multifractal, okay? And presents some very peculiar way of clustering. You can, I will probably skip this because it's a bit technical, but actually you can model a bit, okay? The type of concentration. Now you just care how they cluster, how they cluster in the system, and also perceptions from law that are not possible, okay? And that's allowing you to get some statistical some theoretical prediction of the exponent that we can use later to make system. So the idea is the following. So I didn't have time to explain the last slide. It's technical, but I will skip it. But the idea is that the turbulence, at least in a quantum system, like we can extrapolate to a classical fluid, is a mixture of two effects. On the other hand, I need correlation between these processes in order to get the scaling of the system, okay, to observe the prediction. And this gives me the polarization, the vortices give me the Kolmogorov scaling, okay. On the other hand, they are not homogeneous in space, they are non-homogeneous in a very intricate way, and that gives me the multifractality and the turbulency. And when you put it together, you get turbulence. And what is nice, okay, well, we have data and we can play a bit with this to check, okay? So here I'm showing the NL spectrum, here is this.
Can you explain a bit more what is fractal clustering?
Yes, that the concentration depends on the moments. Okay, so typically a fractal, you look at that the house of dimension or B2. The simplest way of characterizing a fractal, okay, is by looking at the probability of having two particles, two things at a scale smaller than r. Okay, this means if let's say we are at dimension 2, to make things simple. Okay, if the distribution is Poissonian, okay, so they are completely homogeneous. Okay. Typically, this will be proportional to the area, plus square. Okay. Indeed, when you take the limit of small r, okay, compared to the size box, this is scale like r to the d2, okay, where d2 is 2 for a Poissonian distribution. If the system is fractal, okay, imagine that it's a fractal that concentrates in lines, okay. Then if you do the same, it will be scale like r to the power 1, which is the dimension of the line. They are just concentrated in cluster of size 0 in points, the dimension will be 0. Okay? And can be any number between 0 and 2 for a cluster. And this is related also if you want that if you do count box counting, okay, to the mass square that I have in the system. But you can also get if I now I want to compute the mass Q, the mass 4, okay, and each of these will scale to the power B1, B2, B3, B4. Okay? And like normal clustering, you have a D, which is not the dimension of the space. Okay? But if you look at the mass squared, it will be twice the mass. In multifractal clustering, you have a nonlinear function. And it's not something very unusual. If you look at the pollution in the atmosphere, okay, emitted by a chimney, you have a turbulent flow. The distribution in space is not a homogeneous at all. Okay? It's just not classic to cluster, it's multifractal cluster. Okay? It's a kind of complicated way of it's not enough to look at the lower order statistics to describe the concentration. What I was saying, okay. So I can play, and I can check a bit this idea. Okay? And what I do, I know where the vortices are, and I can completely shuffle the sign of the vortices. So I can destroy completely the correlation, okay, but keeping the position. Okay? And then I can do my measurement. If I do that, okay, I get a different power of spectrum, which is normal, okay, but I get something that is a different scaling. Okay? I recover, for instance, here I see some intermittency, okay, that is related to the position of the vortices. And if I do the same game of looking at the function of n, I get a self-similar behavior. Okay? But this time with the scaling corresponds with this arrow number. Okay? And basically, if I destroy correlation but I keep the position, I still get something that is intermittently highly non-trivial, telling that really how they concentrate, they give me some very strange. Okay? You want in complex fractal, okay, will be a straight line, okay, with the wrong power. Not the power given by this, but with a different power. Okay? That would be just a simple monofractal. Okay? And basically we can account for this, and we can understand this is really a composition for square effects. Okay? Just to end a bit, the main takeaway message, okay, that somehow classical and quantum terms are very similar, despite the very different equations that are described. And what is nice that quantum terms being discrete is a very nice system to apply some probabilistic tools. And you can use Markov chain. You will expect to have very large, to apply large deviation very naturally. Okay? What I taught today was mainly published in this two papers. Okay, but then we collaborated with some experimental with Tallahassee, we analyzed data from helium, because more recently we studied the same problem. So, thank you for this. I hope it was not too dense. You could get something. I mean, there are many concepts.
Thank you so much. Comments?
So all of your simulations.
And then I do a minimization process that actually make me a local ground state. Okay? So I'm starting from a kind of local. Okay? It's out of equilibrium. So actually I will develop a lot of turbulence because this work will reconnect. Each time you have a reconnection, okay, you have a sound that's okay? And this is an irreversible process. So in the end, what's going on? You start from something where there's no sound. The vortex go reconnect with sound. This goes on, goes on, goes on. And what you have is an irreversible transfer from the kinetic energy related to the vortices to all other parts of the energy. And now if you look only at the kinetic energy that comes from the vortices, this is what we are more interested in. Okay? That will be
It's not your initial state, the initial condition very special, right?
yes.
So it is.
So it's well, I don't have why it looks. This is probably not very far from the initial condition. Okay. And how do we choose it? Okay, there are well-known classical fields. It's called an ABC field. Okay, it's a very helical. And we actually minimize the equation such that the lines mimics as close as possible this classical field. Okay? And this is only minimizing some equation. Okay? I didn't there is a way of preparing the condition such that at large scale you have something that looks classical.
So evolution or initially can be stabilized quick, not possible. So
It is quick, but simulation is still big. Even if it's quick, it's costly.
yes,
Okay? But yeah, there is all know-how. You need to know how to prepare the initial state in order to get turbulence. You just put noise. It's more likely that you will get a kind of wave turbulence. That's another. But it's nice with circulation, okay, that I'm looking at the integral of the gradient, okay, that all what is compressible spreads out. And only what remains after completing the loop is the contribution of vortices. So this is also very, that's actually what was a very nice observation.
Viendo un poco de efecto limpia, así que perdón si la repito algo que en la presentación. Pero no, pese a que dijo que los fluidos clásicos y cuánticos son similares, en una parte ponía que si, como pregunta la hidrodinámica, ¿el fluido cuántico no se considera entonces dentro de la hidrodinámica o sí se considera?
Sí. No, depende a quién le pregunte.
Porque claro, la
Si me
hidrodinámica...
pregunta a mí, digo que sí.
Y como
Si
la
le
hidrodinámica-
preguntas a alguien de probablemente ingeniería mecánica muy tradicional, te va a decir que no. Pero sí, tiene un comportamiento. La ecuación que lo describe no parece ser una ecuación de transporte. ¿Okay? pero sí tiene una aerodinámica especial. Lo que pasa es que hay que interpretarlo un poquito más, pero sí tiene todas las leyes se comportan muy parecidos. Tú puedes cambiar la variable y escribirla como ley de conservación. ¿Okay? Solo que hay que tener cuidado con el mapping los dos, ¿okay? Porque la fase no está definida de una es un poco singular, pero para generar una intuición, sí, es una cosa muy difícil.
Entonces no estaría tanto el tema de probabilidad, como se permitía la cuántica, por así decirlo.
No, porque como dijo
Bing.
la ecuación que uso es la ecuación de Física. ¿Entiendes? Toda la parte de circulaciones cuánticas ya no está. ¿Okay? La ecuación que creo que viene de la segunda cuantificación. Viene de una aproximación específica en cual tú puedes, dice que hay muchas partículas y una que se llama semiclásica, en la cual tú desprecias todos los efectos cuánticos, lo que te permite reducir esa ecuación. Si no, esta ecuación de referencia en vez de sí, todos seríamos de la otra. ¿Okay? Sería una ecuación lineal en un espacio gigante. Pero en esa cierta aproximación, que es mucho más fácil que la clásica, te permite tener una ecuación de medidas parciales y que es la ecuación que todo el mundo usa. Y después tú puedes empezar a agregar correcciones que vienen en primer orden, en theory, y diferentes cosas que pueden empezar a tomar sistemas más complejos cada vez. Pero sí, hay una mecánica cuántica, pero una aproximación detrás que te permite tener eso.
¿Algunas preguntas por Zoom? Totally bilingual. Totally bilingual. Puede ser en español. Parece que no hay preguntas de Zoom por acá. No.
Yo solo, pero de ignorante. Muy interesante.
Where did you do the experiment?
The experiments were done in Tallahassee by the group of Wei Wu.
Yeah.
They are done with helium, okay, and that actually is a grid glass.
Couple years ago.
Yes, this couple of years ago, the data was even a little older. The data was in 2020. Now I'm collaborating, have a new project with a colleague in Grenoble, in France, which is doing more vortex dynamics in helium. So it's a rotating technique. So I don't know if you know, but if you rotate a classical fluid, okay, so you will expect to have parabolic pressure. Okay? You are required, the fluid is required in the moment. If you do it with a superfluid, nothing should happen. Okay? But it's because actually there's no friction with the container. Yes. But this is not the case. Okay? Indeed, the system tries to mimic a bit what's going on, but cannot rotate like that. So instead of creating that, start creating vortices one by one by creating a lattice. Okay? Or an amplitude of lattice. And so this experiment in Grenoble is actually that. It's a cryostat. Okay, it's a rotating cryostat.
It's like you're making a real increment of your initial condition.
Yeah. So they have this rotating cryostat and a technique to visualize vortices in real time. Which is a kind of very technological challenge. So experiment with helium is at 1 Kelvin, 1 and 2 Kelvin. So it's everything, and it's a superfluid, so it leaks. It has no friction, so it leaks. But people know, experimenters know how to do this.
Yo tengo una pregunta, pero por curiosidad, sobre los experimentos y las cosas que se han hecho, se piensan hacer, porque están los experimentos con helio en la fase superfluida. ¿Sí? Y tú dices, claro, uno puede hacer cosas interesantes como rotar, pero también, por ejemplo, uno podría introducir campos magnéticos si el superfluido tiene alguna característica magnética,
Sí,
y hacer como este efecto de la fase de Pires, como que te da, como que va a depender mucho en qué sentido está.
Bueno, la rotación un poco juega el mismo rol.
¿Es posible introducir esos campos externos en el comportamiento?
El helio no tanto, lo que existen son condensados de dos particulares.
Sí,
¿Okay?
que es algo que
Y eso sí tienen y están muy de moda. Han retomado mucho peso en los últimos 5 años. Está el grupo, justamente el grupo de Vitayes y Centro, de hecho, muchas contribuciones teóricas y también las aplicaciones. Y tiene una gran gracia que los procesadores circulares responden al campo magnético. ¿Okay? Y cuando tú los comprimes, ¿okay? Lo haces casi 2D. La relación de expansión de las ondas, ¿okay? Cuando entonces la teoría efectiva, me muestra un mínimo botón. ¿Okay? Y es súper entretenido el concepto teórico porque la relación de expansión se parece a la de Helio, ¿okay? Solo que ellos pueden controlar experimentalmente la altura del mínimo botón. ¿Okay? Y es más entretenido que el mínimo botón puede tocar el eje y eso proporciona una estabilidad muy conocida y genera un super, lo que se llama un supersónico. ¿Okay? Que otro ground state con un lápiz que eso es realmente el experimento actual, ¿no? Claro. O sea, los últimos 12 años. El problema de los condensadores es el tamaño de los experimentos, realmente son bastante pequeños. Y en helio los problemas son las medias. Pueden ser grandes, son súper difíciles en la medida pequeña.
Algo que se me ocurrió viendo la presentación, que en el fondo con esta idea de que hay pequeñas diferencias entre un fluido clásico y un fluido cuántico. Y se supone que tú lo que quieres hacer, o sea, lo que uno quiere hacer, digo, lo que uno quiere hacer con los fluidos en el fondo, pensando en un sistema clásico y un cuántico, es por ejemplo ver fenómenos de cuando uno ve de coherencia, algo cuántico que transita algo clásico. ¿Se han hecho estudios como pensando en eso, como cómo transita de un estadio al otro?
No creo, yo creo que debe ser muy difícil porque aquí yo ya parto una cosa difícil.
Sí.
Claro.
Y partir para poder, si no parto de ahí yo creo que no puedo hacer nada.
Claro.
Hay muchos cuerpos.
Es demasiado, entonces
Claro.
Y las escalas son muy...
Probablemente se requieran nuevos métodos.
Sí, yo creo.